Assalamu alaikum, dear students. Welcome to the lecture of hydraulic structure. In this lecture, we will discuss about an example and their solution, which is in which we check the stability of a hydraulic structure, which is the gravity dam. In my previous lecture, I have already studied about that what is hydraulic engineering and what is the importance of hydraulic engineering and what is the use of hydraulic engineering. Basically, in hydraulic engineering, we are concentrated and we are focused on the hydraulic structure, and we check the stability of the structure. We check basically the forces of the water which is exerted on the structure, different type of structure. Basically, in hydraulic engineering, we are specially focused on the open channel flow. Like how is the characteristic of water when water goes through the open channel, just like specific gravity, Reynolds number, critical depth, etc. So all of the things we will find in the hydraulic engineering. The other thing in hydraulic engineering which we find, just like dimensional analysis, model analysis, and different type of equation we derive and find in the hydraulic engineering. Okay, now in hydraulic structure we will check the stability of the structure. For example, in hydraulic engineering, when we design a hydraulic structure just like the gravity dam, so now we check that this dam, if the height of the dam is that much and the water quantity in that dam is just like the height of the dam is 68 meter and the height of the water is 65 meter. Now in that condition, if the dimension of the dam is this, so the dam will stable or not. So basically in this lecture we are interested in this thing. Okay, so now what is hydraulic structure? Hydraulic structure is any structure that is disrupt, stop, and divert the flow of water is called hydraulic structure. Or hydraulic structure is any structure that is submerged, partially submerged, and fully submerged in the water is called hydraulic structure. So there must be some forces exerted from the fluid or from the water which is acting on the hydraulic structure. So basically we are find these things, that what is the effect of the water and what is the reaction of the structure. Okay, so now for the gravity dam is shown in the figure. Check the stability in reservoir full condition considering weight of the dam, water pressure, and uplift pressure. So here in this question we are interested in two type of forces. For example, the water pressure is acting on the dam is horizontally as well as uplift pressure. Okay, so first of all, for the ease of calculation, we will tabulate it all of the equation and all of the data, because there is too much calculation. So when we write here without table, so we will be confused after picking the data from the table. Okay, so here different type of dimension are given in this dam. So first of all, I am going to explain that what is this structure and what is this area. This is the complete structure of the dam. This is called gravity dam, because when we provide this dam to retain the flow of water, to retain the water, we use this dam to retain the water, and this area is called reservoir. Okay, this is the reservoir. Reservoir is a place and depression area where we store the where we collect the water, and then we use these water for different purposes, just like domestic water, industrial water, and for irrigation purposes. Okay, now we are check the stability of this dam, but before starting the stability, it is necessary to know that what is the unit weight of dam material and what is the unit weight of water that is acting on the dam. So the total height of the dam is 68 meter. From the base point to the top of the dam, this total height of the dam is 68 meter, and the total base of the dam is 53 meter, because 48 plus 5 is equal to 53 meter. Now free brood mean this area we provide for factor of safety. So what is factor of safety? Factor of safety mean that the permissible limit for the water is below from the top level is 3 meter, because when water rise up to this level, so we do not allow further water from this level. We provide spillway here in this area, so we open the spillway and water drop down from the dam or reservoir. So when we do not open the spillway, okay, so water will up and goes upside of the dam and erode the dam. So this can be lead to failure of the dam. Okay, so we are interested to avoid the failure of the dam, so that's why we provide free brood in the dam. Now the width of the dam is 7 meter at the top portion, and this triangular area is started from 14 meter of the top of the dam. Now there are two types of triangular area. Basically when we provide only rectangular area, so the load will be acting more. For the increasing the area of the base, we have provided triangular area at the both side of the dam. So this area is this length, the base length of this triangle is 41 meter, and from this point and at this point the length of the dam is 48 meter, and from this point to this point the total length is 53 meter, and from this point to this point the length is 5 meter. Okay, now what we will do in the first step? In the first step we have making a table, and we make 1 2 3 4 5 6 7 columns and different rows. So in first column we will write here forces, and the second one is force calculation, and the third one is vertical forces which is acting on the dam in kilonewton, and the fourth one is horizontal forces, the third one is the lever arm, the next one is movement, resultant movement, and this one is m0 also resultant movement which is acting horizontal are the ph and pu. Now I am going to explain these terms, that what is this. So this is the irregular area. For irregular area it is very difficult to find their area. So for the ease of calculation we will divide this dam area into different portions. Like in this dam I have provided 3 sections. The section number 1 is triangular, the section number 2 is rectangular, and the section number 3 is again triangular. Okay, the first triangle name is W1, the second rectangle name is W2, and the third one is W3, which is the force of this dam acting downward, because this is gravity dam. All of the dam acting on gravitational force. This is standing here, this is standing here and stable on the ground surface due to gravitational force. So that's why the dam weight is acting downward. So first of all we will find their area, and then we multiply the density of these area. So it is necessary to know that what is the density of dam material and what is the density of water. So the density of water in this condition is 10 kilonewton per cubic meter, and the density of the dam material is 24 kilonewton per cubic meter. Now first of all, if we are interested in only the dam, this table is show the and represent only the dam calculation. So the first one is W1. For that we will find the triangular area, and then we multiply the density of the dam material. So it is necessary to know that how to find the triangular area. It is so easy, because we multiply just two sides of the triangle, base and perpendicular, then divide by 2. So this is easy calculation, you can find easily triangular area. Then we multiply the density of dam material, so you can get the vertical forces of the dam which is acting on the earth surface. Okay, so this base of the triangle is 5 meter and the height of the triangle is 31 meter. So after multiplying this and divided by 2 and multiplied by 24, which is the density of dam materials, you will get 1860 kilonewton load which is acting downward. Now we will find the area and the weight of this portion, which is W2. So W2 is equal to 7 multiplied by 68 multiplied by 4. So we are 7 is the basically is the width of the dam, and 68 is the height of the dam, and 24 is the density of dam material, And similarly you can find here 41 multiplied by 66 minus 14, which is equal to 44, multiplied by 24, which is the density of the DAM material. You will get this answer. Now it is necessary to know that, for example, this is the DAM end portion. For example, this is the downstream side and this is the upstream side. So all of the forces will be lever arm at that point, because this point we will consider a lever arm. So from this point now we will find every triangle and every rectangle center of the, because when the load coming on the DAM, so this is irregular area, and the summation of all load and the maximum concentration of the load will be here, and a center which is unknown. We need to find the center. Okay, now if we are interested in W1 center, okay, so it is necessary to know that when we want to center of the triangle, okay, so this is the center of the triangle, this is the total length. So if we want from this side, so L divided by 3. If we want from this side, so 2 divided by 3 multiplied by L. Okay, now we are interested from this side, so we will multiply 5 into 1 divided by 3 multiply plus 48, because this is the additional area, additional length, sorry. So you can get the lever arm. Okay, and similarly you can find the lever arm from this point, which is 41 plus 7 divided by 2. Okay, and this one is starting from this side, which is not 90 degree, and the angular side of the triangle, which is not 90 degree, less than 90 degree. So you will get 2 divided by 3 multiplied by 41, you will get 27.33. This is the lever arm. So these all are the vertical loaded, and this is the lever arm. So we will multiply load multiplied by lever arm, you will get resultant movement. Okay, now we are shifted the forces of the water which is exerted on the DAM. For example, this water is apply a force on the DAM. This is the horizontal pressure, and if this water pressure is horizontal, so must be there up left pressure which is acting on the DAM from downside. This is from left to right, and this is from down to upside of the DAM. So we will find the concentration of load of water. So this is the area is rectangular area, which is PV1, and this is PV2. Okay, so how we can find PV1? For PV1, this is the similar and symmetrical area but opposite in direction, same magnitude but opposite in direction of W1. So we will multiply this 500 by 31, but in this point we will multiply density of water, because unit weight of water, because we are interested in finding the weight of unit weight of water. So this will be equal to 775 kilonewton. Okay, which is vertical forces on the DAM. And again we are find PV2. PV2 is equal to 34 multiplied by 5 multiplied by density or unit weight of the water. And PU is the uplift pressure, which is equal to 53, because total base of the DAM, and multiplied by height of the water, which is 65 meter. Okay, multiplied by density of the water, you will get this answer. But this will be negative, because this is opposite to the DAM. Okay, and we will find the pH, which is horizontal forces of water. So we will take this triangular area and the height of the triangle, which is 65 meter, and base will be equal to 65 meter. So 65 into 65, we will get 65 square divided by 2, because triangular area, and multiplied by 10 density of the water. But this is the horizontal force. You can see this column is blank, because there is no horizontal forces, and only this one force is acting horizontally on the DAM. So this one is acting horizontally. Okay, now what we will do? We will do the lever arm. Lever arm for this area, for this area, for this, and for this. Okay, so this one is similar to this, but we will multiply 2 divided by 3, because this is the 90 degree side and this is the another side, which is less than 90 degree. So 48 plus 2 divided by 3 are 5 meter. Okay, and for this one 48 plus 5 divided by 2, and for this one is 2 divided by 3 of 53, and for this one is 65 divided by 3. Okay, and again we will similarly multiply these terms, and only this is m naught, Pu and Ph, because this is the water pressure which is acting on the dam. So we will get our data in the tabulated form, and we will sum up these all columns such as Mr and M naught, okay, and Fv, Fh, okay. So we will add these four columns and we will get the result of summation of these forces, okay. So this is the Fv, which is 25,102 kilonewton, and this is the horizontal forces 21,125 kilonewton, and the summation of movement is that much and M naught is that much. Now we are able to know about that what is the magnitude of the forces which is acting on the dam, and what will be the reaction of the dam, and if this is the movement and these are the forces. Now we check this dam is stable or not stable, okay. So for that we will first find the eccentricity of the loads, okay, that where the all load acting. Now question arise in my mind that what is eccentricity. Eccentricity is the simple thing, because for example this is my hand and force applied in the center of my hand, okay, or this consider a beam and a force applied in the center of the beam. So this is the eccentric load, sorry, concentric load, because there is no eccentricity. If from the center of my hand I apply the load from some distance from the center, so this distance is called eccentricity of the load, okay. So eccentric load having different analysis and designing method, and concentric load having different analysis and designing method. Now what we will do, we will find the eccentricity of the resultant forces. We have formula E is equal to B divided by 2 minus x bar. What is the x bar? X bar is the location of the force which is acting on the center of the dam. So x bar is equal to summation of Mr minus summation of F naught divided by vertical forces. So we will put here the data from these table, okay. So x bar is equal to 153 meters. So it means that from this point your load will be acting and 153 meter, okay. Sorry, 153 meter is x bar. We will find eccentricity, then eccentricity show that what is the value of the forces which is acting on the dam. So B divided by 2 minus B is the base of the dam, 53 divided by 2 minus 1, 15.3. So E is equal to 11.12 meter. What does it mean? It means that from that point and that point the load will apply to the center at 11.12 meter, okay. Now we are able to find our checks, our factor of safety against the dam. So factor of safety against the torsion is equal to E less than B divided by 6. If we find the value of E and we have the value of B, so we can easily check. We will divide it B on 6 and compare with the help with the value of E. So B divided by 6 is equal to 8.83, which is not greater than eccentricity. It means eccentricity is greater than that. So our condition is not satisfied. This dam will fail in the torsion. So shear stresses of heel. So stresses of heel will be greater than 0. Now what is heel? This point of the dam is called 2 and this point of the dam is called heel. So we have formula gamma is equal to summation of vertical forces divided by B and 2 1 plus minus 6E divided by B. Now question arises in my mind that what is plus minus in here formula? What is the meaning of plus minus? When we use this formula in the form of plus, so this stress will be found for the 2, and if we find this formula in the form of minus, we will get the stresses of heel, okay. Now what we will do? We will do first the stresses of 2, which is in the form of plus, okay. Summation of vertical forces divided by B into 1 plus 6 into eccentricity divided by 53. We will get the result of 2, okay. And now basically we are interested in heel. So summation of vertical forces divided by B into 1 minus 6E divided by B, which is minus 122 kilonewton per square meter. So which is not greater than 0. This force should be greater than 0, but in this condition the load, the magnitude of the answer is less than 0. So our condition is not satisfied against stress of heel. Now we are coming toward that what is the overturning factor of safety. Again overturning. Okay, what is overturning? Because this load when applied to the this dam, so this dam will overturn. Okay, so we will check the stability in that condition. So we have formula summation of m naught divided by summation of mr divided by summation of m naught, which will be greater than 2. Okay, so this when we do this, so this is less than 2, so not safe fail. Okay, so we have another check, summation of mr greater than m naught, then okay, and torsion. So summation of mr greater than m naught, so this condition is satisfied, so the dam is safe in torsion, overturning, sorry. Now the third point of main concentration of factor of safety against stability. When we provide this type of dimension to the dam and that much water horizontal pressure acting on the dam and the uplift pressure quantity is that much, the dam will stable or not stable. Okay, basically we are checking in this point. So factor of safety against stability, we have formula. Micro summation of vertical forces plus B into Q divided by summation of horizontal forces. Now what is micro and what is Q? For the gravity dam, the value of Q is constant, which is 1400, and the value of micro is 0.65 to 0.75. So we take average of these value, summation of these things. So micro is equal to 0.7. Okay, so this value should be greater than 1. If I put it all of the value in this equation, so we have get the result 4.31, which is greater than 1. So our condition is satisfied. Okay, so this dam will be safe in factor of safety against stability. Okay, so this is the example of hydraulic structure. I have solved in detail and I have explained every point in every detail. Okay, so if you have any question, if you have any queries, you can comment and I will reply you. Okay, thank you.